So, good afternoon, everyone. My name is Vittorio Ziparo. I'm one of the two founders of Algorithmica, a high-tech startup, an Italian high-tech startup, which is something which happens seldom. So in this talk, I want to present to you Rovina, a project where we use artificial intelligence and robotics to help archaeologists to explore and build 3D models of archaeological sites. This is a fairly big project. It's a 3.5-year project. We just finished year one. We have been co-funded by the European Commission, and we have an overall budget of approximately 3.6 million euros. So it's actually a moderately big project. The project is executed by a consortium of 6 partners. There's us, Algorithmica. Then we have 4 top European universities that include the University of Freiburg, which is the coordinator, La Sapienza here in Rome, the University of Leuven, which is in Belgium, the University of Aachen, which is in Germany, and a non-governmental organization, which is... Okay, and a non-governmental organization... I actually have 2 microphones. I don't know which is the right one. Può alzare un po' il volume? Sì. And the non-governmental organization, which is called ICOMOS, which is the International Council on Monuments and Sites, which is in charge, is a consulting body for UNESCO, is in charge of the monuments and the sites worldwide. Our goal is to help these people, the archaeologists, in 3 main tasks. One is exploration. You will not believe, but there is a huge amount of underground cultural heritage which is not explored. Here in Rome, we have the catacombs. There's about 150 kilometers of completely unexplored catacombs. And where they are explored, we have maps which are hand-drawn, which are clearly not something which is accurate. We then they also need to monitor underground infrastructures, because if you don't monitor them, you're not aware of potential risks, and then they collapse. This is a Domus Aurea in Rome, the House of Nero, but you have seen what happened to Pompeii just recently. And third, they want to have a digital archive of such cultural heritage sites so they can pass on to future generations and they can disseminate this cultural heritage worldwide. Here's an example of such an effort in the case of museums, where Google, with the Google Art project, did the 3D maps, well, 2D&1/2, we could say, maps of the museums and exposed them via their OpenStreetView technology. And currently, what the archaeologists do to build these maps, to monitor these sites, and to build these models is they go around with these objects. They're called LiDARs. They're 3D laser rangefinders, and they place them nearby the site. They acquire some measurements, then they move this LiDAR somewhere else. They acquire other measurements, then they sit down, like this, around the laptop, and they try to match these measurements like a patchwork, like a puzzle, to build up a model. And these models look something like this. And this process is really expensive and slow. It takes like 6 days to do a room of this size. And it takes many people. And the result, it's not so cool. I mean, it's useful probably to them, but it's not something which has all the information you would want from a 3D model. Our goal in this project is to build a robot, here you see an early prototype, which can go in the archaeological sites and automate this process of building 3D models. And we want to do this in a faster way. So while a human can take maybe 5 days for this room, this robot would take the time to go from here to there. And that's mainly because all the processes in the pipeline are completely automated. So there's no humans involved except for minor qualitative things. We want to build better models because humans are constrained to small environments because of computational problems, while the technology we build here can span over very huge sites like the catacombs in Rome. And these models will be more accurate and richer. There will be models like you would expect a 3D model, like in a video game. Very accurate, very immersive models, and I will show some pictures of them right now after a few slides. And finally, this approach is safer because often it's very dangerous to go and take a scan inside a catacomb where things can fall down, or in a building which is about to collapse. So we want to provide a better tool which is faster, provides better 3D models, and is safer for the end user. We are performing 2 case studies in the catacombs of Rome and Naples that we have chosen mainly because they're a wonderful example of this technology. They're huge, they're extremely rich in geometry, you can see up here, but also in texture. They have very nice painting and frescoes. And they're also very a very hazardous environment because things can collapse on the operators, and there's a high percentage of radium which can lead to you can get cancer out of radium because it's radioactive, while the robot has no such risk. The basic idea is to provide a system which looks much like a video game. So you want to sit down with your laptop, have a joypad, and remotely operate the robot while it's going around and acquiring the data within the catacomb. You will have a 3D immersive environment. We call this multimodal, which looks much like a video game. You will have mini-maps, you will have snapshots, battery status, and whatever you need. The system is also smart enough to be able to recognize when something is interesting, and it could say, hey, operator, you know, there's something interesting up here. Go and check it out. And once you're there, you can actually annotate and put some semantics in this model saying, you know, this is a pot, this is a piece of stuff which comes from the 2nd century after Christ. This vision is very nice, very appealing, and can work in a wide number of scenarios, like in a church, like in a big house. But in a catacomb, as soon as you turn the corner, probably wireless connection is lost and you don't have any such model anymore. So the interface recognizes this, the system recognizes this, and downgrades the interface from a multimodal, fully teleoperated to an what we call a supervised interface. And to keep contact with the base operator, the robot starts dropping this kind of device, which are called Zigbees. This can be taught as small repeaters, which are left down the way, maybe 500 meters, which automatically configure themselves so that they have a multi-hop network. So when I send a signal, I go to the closest Zigbee, this one sends to the closest one, and until it gets to the operator. And they're also very cool because they have a very long battery lifetime, something like 5 years. And they can stay there for a long time, and while they're there, they collect data. They collect temperature, pressure, humidity, all sorts of data which can be streamed back to a base station for controlling what's going on. They're actually often called sensor networks for this reason. So once we have this, this network in place, we will have probably a lower bandwidth because these devices have just a small bandwidth and higher lags, and you will not be able anymore to control directly the robot. You need a different type of interface, what we call a supervisory interface. I don't know if you ever played to StarCraft or similar games. You have sort of a bidimensional map. Black is where you've never been, and the other colors is where you're being. And green is a traversable area, yellow is a challenging one where maybe there are some stairs, and red is a dangerous area. And what you do, you just click on the black area, and the robot autonomously plans a path, finds his way through the ruins, and reaches the place. And while he's doing this, the map here grows slowly and gives you more information. Clearly, you don't have much detail in this map, but the robot is smart enough to understand if there's something interesting, and he could say, hey, you know, I've seen a cross on a wall. It looks like some interesting archaeological thing. Do you want me to send a low resolution picture? You can say yes, and you get the picture. And then based on this picture, you can give more input and say, go there and search more. Nevertheless, this robot has something like 7 hours of autonomy, and you will very quickly run out of Zigbees. And at this point, the interface from a supervisory one becomes a dialogue one. We call this HAL mode, and this is HAL. Because you actually start, you know you will lose contact with the system, so you have to talk to him, and you have to say, hey, go down there in this dark area and come back maybe after 20 minutes. So the robot goes autonomously there, reports interesting things, takes pictures, comes back and tells you, here's the new map, here's the new pieces of information. What shall we do now? Shall we proceed again there? Shall we go somewhere else? And so on. And this is, and once the robot came back, we have a load of data. We actually collect 2 terabytes of data per hour. All this data is then post-processed to build really cool 3D models, which I will show just in the next few slides, which are uploaded on the cloud and are made available through services for the general public by providing high-fidelity virtual site viewers or high-fidelity virtual museums, for historians which can have which can do data mining in this data, can look for all the pots which have been done within this time span and have these characteristics, and for engineers which can look to how things changed over time, because we can actually send this robot more than once in the same place and then acquire the models through time. And in this way, we can check if a crack became bigger, a wall moved a little bit, put triggers there to check dangerous area, and then come there and do what's needed for not having the whole thing to collapse. Now, this is the vision we have for the project. And this project has 3.5 years of lifespan. We just finished the first year, and we already have some preliminary results, which I will present to you. So when we started, the first issue was, how can we find a thing which can navigate into the catacombs? I mean, the catacombs are hell. There's a lot of debris. There are stairs, small ones, big ones, holes, and there's narrow passages. And the first thing you think is, who has a cool remotely operated car which can go everywhere? The military. So you go to them and you look at these big iRobots with flippers, but they weigh like 200 kilograms. They are huge and they cannot fit in a catacomb. It took us a while until we found this platform, the red one you see down here, which is built by Mesa Robotics. It's a teleoperated one, but you can see that in this video that it can tackle practically all the obstacles. So we can go up a steep hill. That's okay. Looks fine. Then it can maybe tackle this kind of obstacles. Oh, these are no problem, you see. It's actually a very robust platform. It's not afraid of falling down because it's a robust one, it's a medium range one. And it can go through all sorts of debris, like this ones, with no problem. And it can also, it really has to be very strong because we have to put on top of it a lot of things. You see he's bringing up to 100 kilo stuff. A lot of stuff to be able to make it an artificial intelligence machine. Computational power, sensors. We had to put an additional 30 kilograms of payload. And well, now this is the military part. Now you'll see that's recognizing bombs and actually shooting down a door, but that's not how we use it. We have another purpose, you see. This is how they use it. Yeah, that's not how we use it, or the catacombs will collapse. So once we have a base, then we had to decide what to put on the base. And this was a very long process, and if you want to have a few extra slides about this, but there's really, you can see a hell of things here. Things from custom electronics to 2 laptops to a whole bunch of sensors. There's Arduino too for the makers in here. There's only Mexino. There's this laser rangefinder and much more. And as hardware is tough because you make mistakes, and when you make a mistake, it's a big pain to recover. It's not like a bug on the software. So we started through simulations and went through a big number of steps. And when we had this thing, which was really shock-proof and really powerful, I started driving it like crazy. And like I want to do the same thing, jumps. But what happens is that when you drive it as crazy, then all the data you collect is really noisy and shaky. And at the end, we had to settle down for a cruise speed, which is more or less this one. This is an early prototype we assembled in Germany. This means the robot will not run as hell because it must be stable. Here's climbing some stairs. And when you're going at this speed, it has this type of movement going up and down, which is not completely wanted. But you can see it's bringing up 30 kilograms and it's not feeling nothing. Actually, at the end of the talk, I will challenge one of you to stop it. And I think it'll bring you out of this door. It's a really powerful robot. We didn't still find the limit to the torque it has. There's Daniele and Marco, 2 engineers working on the project here, which are here teleoperating it. But clearly, the aim is not to have it fully teleoperated, at least not always. The goal is to have a system which is smart enough to drive on its own. Now, I tried to keep the talk simple enough not to get too much in the detail of the AI part. I've seen some of my former students when I was teaching AI here, and I will not go into those details, but I can tell you that there's a lot of AI in here, and at least for this mobility, we have capability of autonomous exploration, so the ability of deciding where to go, how to get there, so planning the path, deciding how to execute the path and overcome obstacles, and how to deploy these devices, which have several different trade-offs. And once we had this preliminary autonomous robot which could navigate in the catacombs, the next question was, how do we build a 3D model out of it? And it turns out that there's two things we have to do. We first have to build a skeleton, and out of the skeleton we have to put flesh on it. So we have a two-sided approach. What do I mean with a skeleton? We have on top of the robot, maybe I can show it to you up here, this very fancy robotic eye. It's actually an eye which is rotating very fast and has a laser on top, which is collecting measurements around. These measurements are called point clouds. And it can build models which are more or less like this. They're not perfect, meaning that they're dots, so there's some emptiness in them and there's no color, but they give a geometrical understanding of the structure around you. Once you build this, and you build this while you're moving, the problem is that the naive approach is, I build this point cloud, I do a step, I measure my step, we have odometers inside, and then I get another point cloud. I know how much I moved, I can fit them. But this fitting is not really trivial because there's noise in the, both in measuring the movement and in the laser itself. So what happens is that the scans in the place where they overlap have some misalignment. And what we have to do is we have to find a way to match them, which may sound trivial but requires some rigid transformation. There's a lot of points, and there's some, and it's not trivial because it's not geometrically pure. You get some errors, so you're not sure which is the best configuration, which matches. And the algorithm which does this is called, this thing is called point cloud registration, and we developed a very new algorithm which can do this very well. You can see here a sequence of scans which are built, as I told you just before, so just scanning, measuring, scanning, measuring. And this is a corridor. You see how deformed it is and all the outliers you have here. With our approach, PWN, which again I will not explain in detail, but I will just show you the result, we can, in real time, very efficiently register these point clouds so that they're neatly aligned one after the other. And this is already a great result for the archaeologists because the most time they spend doing this, getting the point cloud, moving it, and manually trying to fit them together. This technique is very good, but works on a limited space. In our project, we want to model huge areas like a catacomb. And you see here the catacombs of Santa Priscilla. So this white one is the catacomb, which is huge. And at the very beginning of the project, we went down with a preliminary robot mounting this sensor, which you can see up here, which is more or less a Kinect, for those of you who know the Kinect. So it's a depth camera. And we said, let's see what we can do with a Kinect, which produces point clouds just like the laser, and build them up, just by smoothing, as I showed before, just by point cloud registration. This is what happens. The map we built is, has a duplication. So we have this corridor which is seen twice. Because when on a small scale you have a millimeter error, or an angle of 1 degree error, you can't even notice it. On a scale of several kilometers, things diverge very fast. So we tried to add more sensors, and we add this fancy IMU. This is an inertial measurement unit. It's a device which measures accelerations on the 3-axis, like the one you have on the phone. But this one costs 4,000 euros. It's just a more complex one. And even with this accuracy in the measurements, you know, the measurements tend to have more decent structure, but still there's duplications because you will never, and this is one of the lessons of robotics, remove noise from data. You always have some small error. What we have to do here, and what we do is, you have to understand you're coming back to a place where you have already been. So you have to say, this is the same corridor as before. And if you do this, then you're able to produce a consistent map. And this thing is very easy for us humans, it's very hard for computers, but we luckily managed to do it. And once we have a consistent map, we have almost the skeleton we're looking for, but we still miss a piece because we would like that if we measure here this distance, and it's 3 kilometers, here it's not 3 kilometers and 100 meters, it's exactly 3 kilometers. And to do this, we have to, what we do is we, this is scary math, but it's just a way to say that we do complex mathematical calculation, we do optimization in order to take into account all the measures we have, all the uncertainty, all the error, and build a map which is accurate to the centimeter. And here there's actually the data from Santa Priscilla when we went there, when they connect, you see he's moving and he's collecting point clouds for doing the skeleton, and he's registered them, and he's optimizing from time to time, trying to build a skeleton for a model which is consistent. This is just the last part because it was a huge run and it would take too much time to show you the whole thing. But you see the point. He moves, he measures, he aligns, he optimizes, he puts things straight, and when he finished, what he has done is a very accurate 3D model, which is a good representation of the catacomb under inspection. And this model here is what we call the skeleton, although the final skeleton will also have laser data that will be more accurate and will have ceilings. Like here, there's no ceiling because the Kinect cannot see the ceiling, it's too high. So once we have the skeleton, we need to add the flesh. We need to add the details. We need to fill the gaps. And we do this by using cameras. We have very fancy cameras which are able to take pictures of the same thing from different point of views. And within this context, we use a technique used called structure from motion, which is capable of building small but very accurate 3D models of the environment. We actually have built a custom camera array which is able to do this, because there's a lot of issues with how to acquire the images, how to use light, how to synchronize the shutters. And the results of this flesh, what the flesh looks like is something more or less like this. So it's a 3D reconstruction which has color, it's dense, there's no hole in it. It's pretty accurate if you look at the level of a room. So at the level of a room, not the specific one because this was not using proper cameras, but you have an accuracy of 1 millimeter. So if you see a crack of 1 millimeter, that's the real size of the crack. And clearly it has color, which gives it a completely different appeal, a completely different understanding of where you are. Although it's not perfect, can you see here, this line here, this like light and shadow? It's not perfect because the robot carries his own lights on board, and I'll put them on. And when you take pictures with those lights, these lights cast different shadows, and the surface is not uniform. And that's what you have to do. You have to remove these lights, and it's not a perfect process. And by removing this light, you forget what was the property of the material. You're not able anymore to reconstruct the exact color. And if you see this color looks, this is the under the skin, is slightly synthetic. It doesn't look real. It looks like if it was by a gamer, it was modeled. It does not look like a real table. So we looked into this problem and said, how come these colors are not so true, even though we have cameras here? And so I finish. And so we looked at the picture. If you take a picture, this is a piece of a wall, different pictures, and try to patch them up in a 3D model, what you see are shadows, lights, because each picture has its own light, has its own point of view. And what we would like is to have at least something which looks like this, which comes from a uniform lighting, which has a uniform lighting on top of it. And the way we did this was by using machine learning and being able to understand what are the materials embedded in this wall. There's some bricks, and there's some other stuff, which I apologize, I don't know what it is in English. And once you know the materials and you know some of their properties, you can reconstruct the way light reflects on it. And you can put synthetic light, which looks actually like real light. But this, so this model helped us to build, other better pieces of flesh, which have a more realistic coloring and a lesser lighter effect. Still, there's something weird again, because it's like there's a uniform light here. It's not like if there's a source of light which gives different reflective properties in different areas. It's like if you're in open air in a sunny day. It's everything uniform. But in a catacomb, you should be able to reproduce the way that things reflect light from different angles. You should be able to reproduce the reflective properties of materials. And this is a challenge way beyond this one, because it's what we try to learn here called BRDFs. It's a model which tells you for every possible source of light and every possible point of view, what is the intensity of the color that that material will give. Again, we do this with very advanced machine learning algorithm. And here we see, I show you an example of this. So you get here what we call a pig tablet. And this is the old way we do this. We took away light, but there's no reflective information in it. Now, you can see that these two things are, although this looks nice, they're different. You see, this one has a stronger color. It reflects light in a very peculiar way, while this is flat. You see, also the 3D textures, because of this, are quite flat. We would like something which looks more like this. And this actually is the 3D model within the reflective properties. And this is the old one. You see what, I don't know if you can see it on the projector, the difference between this and this one. This new 3D model is much more realistic. It reacts to light. It looks real. You see how it behaves? In the next few seconds, you'll see actually this one, our 3D model, with respect to the real life. Can you distinguish them? They're perfectly the same thing. They react to light, they render color exactly in the same way that you would expect in reality. You know this one is the real one just because there's the machine which was used to acquire beneath it. And another example is the Buddha, which is the real one, which is the Reconstruction. Can you tell? Okay, a smart one saw there was something in the background here, but they really look the same thing, right? The gold and the pots really reflect in the same way from different perspectives. So what you have to think is that we'll have, and this will come in the next year, huge models which have a level of detail and accuracy like this. And you will be able to move within these models and observe how things really would look if you were down there in that catacomb you would never been able to be. In one talk, it would not be possible to tell you all that has been going on in the first year. I think I have a few more minutes and I will show you maybe some more slides for the maker side showing what has been going on the hardware. But if you're interested, come and check out the website of the project and register to the newsletter, because we'll be giving updates and more details about what we have been doing, including technical details for the ones who are interested in this type of work. So in this talk, we covered a lot of ground, which was going from explaining how robotics and AI can help to process automation with a concrete example in the catacombs where we can take away the human component that is the dull one, the dirty one, the risky one, and put the robot in the same place. And the result is we get really accurate maps, way more accurate than before, and we have very appealing 3D models which can be used for a number of different options. And in the near future, the next things we will do, we will need to put the flesh on top of the skeleton, so build actually this really wide 3D models, and we will need to validate the interfaces. For this reason, we need people like you who are not robotics experts to come and help us beta test the system and drive it through the catacombs and tell us how you like it, how you use it, if you're able to use it or not. And if you're interested in being an alpha tester, please register on the Facebook page, and if you like the page, we will announce their call for alpha testers for trying the robot. Thank you. So we actually, thank you. We actually had planned a demo, a live demo, but Linux and the projector fight against each other, so we will not be able to show it in real time. But if you want, you can approach the robot and maybe 3 or 4 or 5 at a time, you can try to drive it, you can see what's inside, and you can see the preliminary interfaces we have. Unless you have questions and you want to ask. Yes, please.
create a real site to put in a game?
So I was asked this question by a company who was actually looking for this. Yes, actually, it's probably much more than you would need in a game, because rendering this stuff in real time will be a challenge. So probably, for example, in our virtual museum, we will simplify some of the geometry and the textures. But yes, for sure, that's something you could want to do. Yes?
At what speed the robot go?
So to get a good picture, it's 30, what was it, 30 centimeters per second, yeah. That was what we found, a good average between not getting too bored and acquiring enough information. Any other question? Yes, please.
And, have you thought about using a smaller robot to put Zigbee around?
No, it's actually him who will drop them.
Maybe it's better to separate the tasks. So maybe one robot
Can follow.
the net and another one.
The problem with the small robot is that you need to put them enough energy to move for 6 hours and enough sensors not to get lost and build them up. And it's not. This is not this big because we want it to be this big. It's the smallest we could make. So, but it could be a cool idea if you could have like a big one and the small swarms going around. Any other question? Okay, so if you like and you want to play with the robot, you're welcome. And ask Daniele and Marco to... Oops. Thank you.